Here is a quick intro into rational functions, how to find domain and range and x-intercepts, y-intercepts, asymptotes, all of that stuff. First, let's take a look at the parent function. What is the parent function? Well, the parent function to all rational functions is 1 over x. Its domain is x not equal to 0, because as you can see, you have a vertical asymptote at 0 where the graph does not give you a value when you plug in 0 for x. It has an horizontal asymptote at y equals 0, which also means that we have our range has y not equaling 0 because it does not touch the x-axis. There's no x-intercept and there's no y-intercept. Now let's take a look at domain for all rational functions. When we have f of x equals p of x over q of x, where p of x and q of x are both polynomials, the general rule of fractions is to have the bottom not be 0. Now, because with fractions we don't want the bottom to be 0, we're going to say that our domain is where everywhere where the bottom does not equal to 0. So for example, if I had the rational function x minus 2 over x plus 5, the first thing I would do is factor. This happens to be factored already. And then I would set each factor in the denominator equal to 0. So here we have x plus 5. So we're going to say x plus 5 is not equal to 0. So my domain is all real numbers except negative 5. Here's some more examples. Here we have a function where the denominator is already factored. Remember, with domain, I don't really care about the numerator. All I care about is the denominator. So here we have x minus 5 is not equal to 0. X is not equal to 5 based on this. And here we have 2x plus 1 is not equal to 0. So I'd subtract the 1, then I divide by 2. Feel free to pause and try the next examples before I give you the answer. So here we have another example. Pause if you'd like to try before me. If not, here we go. Whenever I have a quadratic in the form a squared minus b squared, I can always factor this as a plus b, a minus b. Now, please keep in mind that it does not work for a squared plus b squared. Alright? Does not work for that. So here we have x plus 4, x minus 4. So if I put x plus 4 equal to 0, I get, or I should say x plus 4 not equal to 0, I get x not equal to negative 4. And if I put x minus 4 not equal to 0, I get x not equal to 4. Now here's that case we talked about where we have the x squared. Basically, you could call this x squared plus 9 squared. This cannot be factored, okay? And if we set it equal to 0, let's see what happens. X squared plus 81 not equal to 0. We'd subtract both sides by 81. And we end up trying to take the square root of a negative number, which you can't. So therefore, since the bottom will never equal 0, the domain for x, or I should say domain, is all real numbers. Now in this one we'll have to factor, so I need factors of -3 that add up to -2. So -3, factors of -3 are just 1 and 3, those are the only factors. But it has to be negative, so one of these has to be negative. It has to add up to -2, so I'll make the 3 negative. So I have x plus 1, x minus 3, which tells me my domain is x not equal to -1 and x not equal to 3. Now let's take a look at holes. Holes are points on the graph that don't exist because it would cause the denominator to be 0. Holes and asymptotes do not exist at the same point. We're going to talk about asymptotes in a second. If factors in the numerator and the denominator are the same, holes are present. Holes are included in the list of values that do not exist in the domain. So it's one of those x not equal to numbers. Alright, so let's simplify for holes. We factor first, as with most of the things that we're doing, we factor in first. If there are factors that cancel, you put those factors equal 0, and that will give you the x coordinate of the hole. You plug those values in the simplified function to get the y values of the hole, and you're done. So here's our example. We have x plus 1 over x squared minus 2x minus 3. So it says factor first. So we factored that in the previous problem. We got x plus 1, x minus 3. And so the x coordinate of the hole is that x plus 1 equals 0. This is because the x plus 1 at the top and the bottom, they cancel out. So what remains from this is 1 over x minus 3. So since the x coordinate of my hole is at -1, then I just plug -1 into x and I get 1 over -1 minus 3. So my hole is at -1, -4. Vertical asymptotes. Vertical asymptote is a vertical line that the graph approaches but does not touch. Instead, the graph will either go up to positive infinity or down to negative infinity. They occur where the denominator equals 0, but there is no hole. So you pretty much find it the same way. Our 3 steps are going to be to factor first, check for holes, and use the remaining factors to get the vertical asymptote. In the example we did before, where we found out that we had a hole at -1, -1/4, this canceled out. Therefore, although I get my vertical asymptotes from the bottom equaling 0, x equals -1 is not going to be a vertical asymptote because we already established that that's a hole. Therefore, our only vertical asymptote is at x equals 3, which we get from the second factor here that did not cancel out. So you always simplify for holes first and then list your VAs as the rest of the list of numbers from the domain. Alright, let's take a look at the horizontal asymptotes. A horizontal asymptote is a horizontal line that the graph approaches but does not touch. Instead, the graph will approach the asymptote as x approaches positive or negative infinity. They occur according to three possible types of rational functions. The first type is the top-heavy type, in which case the numerator, the degree of the polynomial in the numerator, is larger than the degree of the polynomial in the denominator. This will result in a curved asymptote or a slanted asymptote. For our subject, we're going to focus on the slanted asymptote, which is exactly 1 degree higher than the bottom. Next is the even powered, where we have both the powers being even. The top and the bottom both have the same degree polynomial. That will result in a horizontal asymptote at y equals leading coefficient over leading coefficient. And we have the bottom heavy function, which has the powers on the bottom being larger than the powers on the top. So the denominator has a higher degree polynomial than the numerator. This will result in the horizontal asymptote being at y equals 0. So all bottom heavy functions approach 0. There's no reason to do any math here. That's just the answer. Next up, we have the even power, where the degree polynomial on the top is the same as the degree polynomial at the bottom. In order to find the horizontal asymptote, you are going to get the leading coefficient of the numerator and the denominator and set y equals to that. In this case, as you can see, the leading coefficient at the top and the bottom are both 1. So we're going to end up with y equals 1 over 1, which gives you a horizontal asymptote at y equals 1. For the slanted asymptote, we're going to have to use division. So it occurs when the polynomial in the numerator is exactly 1 degree higher than the polynomial in the denominator. Use long division to find the equation of the slanted asymptote. But in special cases where the denominator is a first degree binomial, meaning you just have x plus something or x minus something, you can use synthetic division. So here we're going to set up our synthetic division. We have a 1 here, -2, and -4. We are dividing by x plus 1, which means we're going to put a -1 on our little tabletop there. So we bring the 1 down, multiply it by -1 to get -1. We add straight down to get -3, and then multiply again by -1 to get 3, and then we add straight down to get -1. If you need more help with synthetic division, we covered a bit more in one of the polynomial intros. So my slanted asymptote is going to be at y equals x minus 3. I'm picking that up from the x right here and the -3. As you might know from dividing, that remainder is -1 over x. And as we explained before, as x goes to infinity, that will start to look a lot like 0. So we're not going to use the remainder. For intercepts, we're going to do what we do for all functions. To find the x, you set y equal to 0. And if you do that with rational functions, what ends up happening is that you get the numerator by itself. This is because if we set it equal to 0 and multiply both sides by the denominator, we end up with just the top equaling 0. If the numerator can't be equal to 0, there's no x-intercept. If you set all x's equal to 0, you'll get the y-intercept. And then that just looks like plugging in 0 everywhere you see x. If the answer is undefined, then there is no y-intercept. In the next video, we'll be putting this all together. We found the domain, simplified for wholes, found vertical and horizontal asymptotes, and found the x and y-intercepts. In the next video, you will learn how to graph.